Well, now I know. Now I know to refresh the page. I'll let people find me. Oh my God, I almost just exited out of the page. Okay. Okay, I can read everyone's chats now. I have live stream. I don't know how I would have fixed my chat though. Okay. I'll let people find me for a few minutes because I think we had like 25 watching or something. Maybe we can do more Q&A until then, and then I'll finish the problem. Do I have dogs? No, I don't. How's the transition from Ohio to California? It was pretty good. So I actually went from Ohio. I went to school in Northwestern, which is in Chicago. So I transitioned to Chicago life first. That was a big adjustment. And then out to California, I don't know. LA is a lot different than Chicago. The weather's a lot nicer. So what's my workout routine? I just go like 3 or 4 times a week. Lift heavy stuff. I like hiking. I don't know. I like running. That's about it. All right, we've got like 21. I'll do one more Q&A question and then we'll be back to business. Mini break. Have you met anyone famous? No. One time I went to Sidecar Donuts in Santa Monica, if any of you guys have been there. It's a pretty good donut place. And while I was there, Timothy Olyphant's where he played that hot salesman that tried to date Pam. So I saw him. Favorite food? Eggs, if that counts. I don't think I've ever had an acai bowl. So I'll have to try. Okay, let's go back to math. Anyway, where were we? We were doing this ridiculous error-bound problem. And I spit up the error-bound theorem, but now we have to find k. How do we find k? We need to understand the n plus first derivative. Like I said, sometimes you get a really easy function like, oh, if it's e to the x, the n plus first derivative is just e to the x. That's really easy. Or if it's something like cosine of x or sine of x, it's hard to say exactly what the n plus first derivative is, but it's always going to be bounded by 1, so you can just say like, oh, it'll pick k equals 1. Here it's not so simple, and we really will have to just sit down and do the grunt work of computing the n plus first derivative, and this will take a bit of work. So let me start doing that. Now, if f is log of x, what is the first derivative? Well, it's 1 over x. What about the second derivative? So this is like x to the negative 1. Power rule says bring down the negative sign and decrease the power to negative 2. So that would be like negative 1 over x squared. What about the third derivative? The third derivative, I would bring down the negative 2 and decrease the power to negative 3. Now, here's something that's come up a couple of times. But anyway, let me back up. What am I doing right now? Like, what am I trying to do? I'm trying to compute enough derivatives so that I can spot the pattern. If I can figure out the pattern, then I can write down what the n plus first derivative has to be. So that's what I'm doing right now. I'm just computing derivatives until I'm confident that I've seen the pattern. Now, a lot of times when you're searching for a pattern, not simplifying is a good thing to do. So here I have negative 1 times negative 2. I know that that's 2, but I'm just going to leave it like negative 1 times negative 2 because that may help me see the pattern a little better. So let me do a couple more just because I'm not sure I see it yet. The fourth derivative, I would bring down the negative 3. Whoops, I was getting ahead of myself. Bring down the negative 3 and then decrease the power to negative 4. I get that. And I think I'm seeing the pattern, but let me do one more just to make it really clear. The fifth derivative would be bring down the negative 4 decrease the power to 5. Okay. All right, I got your emails. Sorry about that. Okay, so I've done enough now. I think I can see the pattern. It's a complicated pattern, but let's take it piece by piece. So like I said, ultimately what I'm after here is the n plus first derivative as a function of x. Okay. Step by step, it's a fraction. I can do that much. Also, there's a power of x in the denominator. So this will be x to some number. And it looks like, if I look at all these derivatives I'm taking, that number matches up if I take n plus 1 derivatives. I'll get x to the n plus 1. Okay. What about in the numerator? I don't know what the renegade dance is. I'm getting old now. Okay. In the numerator, I have something that looks like a factorial, right? There's a bunch of negative signs, though, so I think the first thing I would do is I would factor out all of those negative signs to leave me with a positive factorial. Now, how many negative signs do I have? When I did 5 derivatives, I get 1, 2, 3, 4 negative signs. When I did 4 derivatives, I get 1, 2, 3 negative signs. So if I take n plus 1 derivatives, I'll get negative 1 to the n negative signs. And that would leave me with here a 4 times 3 times 2 times 1. 5 gives me a 4 factorial. 4 gives me a 3 factorial. So n plus 1 would give me an n factorial. Whew. That would be the n plus first derivative. Let's see. What's the best acai bowl place in LA? You'll be fine. Don't worry about it. Okay, so that's the n plus first derivative, but we actually just care about the absolute value of the n plus first derivative, right? So let me continue this over here. The absolute value of the n plus first derivative is going to be the absolute value of this expression, which would kill off the -1 to the n sign, leaving us with n factorial over absolute x to the n plus 1. Holy cow. Okay, so that was a lot of work. Acai Nation. And then Cheney asks, so in which cases would we just use 1 for k? It's really hard to say in general. The one scenario that you can for sure always use 1 for k is if the function is sine of x or cosine of x. Otherwise, it really does depend on the interval you're working with. It depends on the function. So it's a little hard to say. It's a little hard to say in general. Whoops. Okay, so there's the absolute value of the n plus first derivative. What do we need to do? We need to find an upper bound for this thing on this interval. So here's the question. On the interval from 1 to 1.3, how does this behave as a function of x? As a function of x, this thing is decreasing. As you make x bigger and bigger and bigger, these fractions get smaller and smaller and smaller. So a rough sketch of this thing would be something like that. Sorry. Hand side of this interval. The maximum value that this can take is this height. That's what I'm going to call k. So in other words, k is going to be the value of this expression evaluated at x equals 1. Okay. Oh, I want to keep this up here because we still need to use this. So I'm going to erase this unless anyone has any questions about it. I'll say no. So to get k, the red height, I'm going to plug in 1 for x into this expression. One to the n plus 1 is just 1. So this is n factorial. That is our value for k. How did I get the lower bound to be 1? So that came from the fact that the interval we care about is from 1 to 1.3. And the reason why this is the interval that we care about is because b was 1.3 and a was 1. So it's always a and b that determines which interval we care about, if that makes sense. Nice. Okay, so this is a little different than a lot of things that we've seen before. K is n factorial. Feels a little weird, but that's okay. So let's pop that back in here, see what it tells us. Log of 1.3 minus Tn of 1.3 in absolute value is going to be less than n factorial over n plus 1 factorial times, this is like 0.3 to the n plus 1. Okay. Now the n factorial over n plus 1 factorial, I can simplify that to 1 over n plus 1. And what this shows is that in order to make this smaller than this, what we want to do is make this smaller than this. If we can do that, we win. So let me write that down. So it suffices to make, I guess I'll continue over here again. It suffices to make this expression less than 1 over 10,000. Okay, as always, there are many, many things that work, and as long as you pick something and you justify it and you convince me that it works, then 1. And the denominator will be 10,001, which is for sure bigger than the denominator here. So n equals 10,000 definitely works. Just because 0.3 to the 10,001 over 10,001, this number is definitely smaller than 1, and this number is definitely bigger than 10,000. So therefore, this fraction is definitely smaller than 1 over 10,000. Whew, and there we go. That would do it. So that's an error-bound problem. I think a relatively tricky one just because figuring out the n plus first derivative of log of x is relatively sophisticated. I don't know if I would expect that to come up. Probably something like e to the x or cosine of x or something is more probable, but who knows? Okay. Let's do an integral. How many problems will be on the exam? I think 10. I would expect 10. So it'll be about 2.5 times as long as a midterm. So cool. All right, next up, let's do an integral. Let's do the integral of 1 over 9 minus x squared to the 3. Okay. Give me a sec. So actually, Marco specified that you can use a non-graphing calculator. So official policy is that no graphing calculators are allowed, actually. And you know, if we did something like this, in a solution, I would be looking for some justification. Oh, I see what you're saying. Sorry. So even with a non-graphing calculator, could I just use a calculator? Yeah, I guess. Probably. I'd probably be happier with something like what I did, but yeah, that would work. Okay, I need a pick-me-up. I have all this candy that no one can eat because of the whole... I'll let you guys think about this integral. I also have a fortune cookie from Panda. Nacho says trig sub. I agree. Let me see what my fortune is, and then we can go for it. The trig sub I'd probably want to use here. Now again, I guess since this is an open book final, you could probably open up the textbook to section 8.3, and there's a little chart that'll tell you exactly what trig sub to make. But we'll talk about where that comes from and why that comes from. I like Suze's idea to pull out the 9. Okay. I have a kind and generous heart. Oh, sorry if that's loud. Sorry for the crunching. Okay. So I like the idea to pull out a 9 because the whole idea behind substitution is that we want to use trig identities to our advantage. And the identity that I'm thinking of here is that, for example, 1 minus, say, sine squared of x, or sine squared of theta, is cosine squared of theta. That's what stands out to me here, because I see a constant minus something squared. So what I want to do is I want to take this expression here and rig it up so that it looks like that. But my issue is that right now this is a 9, and I want it to be a 1. So what I would do is I would pull out the 9. When I do that, and I pull it through the parentheses, I'll pick up a power of 3/2, and then I'll have 1 minus x squared over 9 quantity to the 3/2 dx. And then this looks more promising. So what I think is now, gee, I really wish x squared over 9 looked like sine squared of theta. And this is what will dictate the trig sub. So in particular, I could solve for x, and I would let x be 3 sine theta. Okay. Right now I'm going over problems that I chose. Talk about those two. I'm about to crunch again, so either get ready if you want to turn it down or turn it up. Okay. Hmm. Hmm. So I make a substitution. Every time we do that, we have to change the differentials, just like in a normal substitution. So if I call x 3 sine theta, dx would be 3 cosine theta d theta. Okay, one day I'll make mukbang with a acai bowl video. Tonight is not the night. Okay, I can do something like that in a sec. Let's finish this one. Oh yeah, so we did our substitution. We can plug everything in now. So this turns into 9 to the 3 halves. I could pull this out front, and 9 to the 3 halves is like 1 over 3 cubed, because 9 to the 1 half is 3. So this would be like 1 over 3 cubed. Integral of 1 over, I've got 1 minus, by construction, x squared over 9 is sine squared of theta. And then dx is 3 cosine theta. Excuse me. Okay, so then the point is 1 minus sine squared theta, like we wanted to use, is cosine squared. So I can run that trig identity. Let's see, the 3 I can pull out front here. I have a cosine on top. And this is cosine squared to the 3 halves. Three over 27 is a ninth, and then this is going to simplify to cosine squared to the 3 halves is like 2 times 3 halves, which is cubed. So this is cosine over cosine cubed, which is 1 over cosine squared. That's what we have to figure out. Oh, thanks. Good catch. 1 over cosine squared is secant squared. And I remember that the derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And okay, we've done the integration. We're not done because we have to switch back to x, but at least we've integrated the function. All right. So continuing on. How do we go back to x here? Go back to the original substitution and draw a triangle. That's always the move. So the OG substitution was x over 3 is sine of theta. And then I interpret what this means in a triangle. Draw a right triangle with angle theta. Sine, so katoa, this is the opposite over the hypotenuse. Opposite over the hypotenuse. So in my triangle here, I've got the opposite side over the hypotenuse. And then I can use the Pythagorean theorem to solve for this side here. This squared plus this squared should equal 9. So it looks like this should be 9 minus x squared under a square root. The point there is, what do we care about? We care about tangent of theta. But now tangent of theta I can just read off from the picture here. Because tangent is the opposite over the adjacent. Pop that in there and we are done. So to finish it off, this thing that we started with is whoops, 1/9 times tangent, so 1/9 times x over root 9 minus x squared plus c. That would do it. Nice. Okay. So, Justin, the question you asked is phrased in kind of a weird way. We can definitely do it. To me, this is really just find the Maclaurin series of 1 over 3 plus some constant times x. But that's a good thing to talk about. So I would phrase the question like this. Find a second order expansion in other words, the degree 2 Maclaurin polynomial of the function 1 over 3 plus beta x, where beta is some constant. And we may as well just find the Maclaurin series and then truncate it. Yes. Well, watching my live stream is a good way to prepare for the final, so that's a good decision. Okay. So I look at this and I think, how can I compute the Maclaurin series here? I would use the fact that 1 over 1 minus star, I can expand this as the sum from 0 to infinity of star to the n if the absolute value of the star is less than 1. So that tells me that this thing, 1 over 3 plus beta x, I want to use this to my advantage. The 3 isn't a 1, so I need to factor out a 3. That would give me beta over 3 times x. And then I want the plus sign here to be a minus sign, so I can make that happen by writing this as 1 over 1 minus negative beta over 3x. Then in the parentheses, that thing looks exactly like that. I can run the expansion and we're pretty much done. So this will be 1/3 times the sum from n equals 0 to infinity of blah, blah, blah to the nth. So this is like negative beta over 3 times x quantity to the n. And then that's the Maclaurin series. So I guess in this problem, they just want a second order expansion, which to me just means a degree 2 Taylor polynomial. So I'll just write down the terms up through degree 2. The term here is 1. The n equals 1 term is negative beta over 3x. And then the degree 2 term is beta squared over 3 squared x squared. To me, that would be an order 2 expansion or a degree 2 expansion. So I don't know where that question came from. Like I said, it's phrased a little weird. To be honest, I wouldn't expect anything phrased like that on the exam tomorrow, but yeah. Okay. I will... I'll take other requests as well if you want, or I also still have more examples prepared, so I can pick and choose some of those. Do what's relevant for the test. Let's see. Everything is relevant for the test. Is the beta stuff? Nah, I wouldn't worry about it. Oh, yeah, I haven't done an invertible function problem. And then... Okay, so let me do an invertible function question, and then let me also look at, Jennifer says number 7 on mock final 1. Let me check that out really quick. If I still have them up. Oh yeah, for 7a, for both of them, honestly, I think for question 7 on the first practice final, probably the intention there, never mind. Those are partial fractions problems. We can come back to that. Okay, Brian asks, proving a reduction formula. We can do that. Let me do an invertible problem, and then we'll prove a reduction formula. So let's see. Example. If I could give you all A's, I would. Unfortunately, it's out of my power. Okay. Yeah, we could do, yeah, so comparison for integrals will not be on the test. We could also find the Maclaurin series for cosh of x squared. Let me do an invertible thing first. Okay, so here's function. And I'm going to try to think of this off the top of my head, so it might be a disaster, so give me a second. Let's let f be Well, let me just make this not too crazy. X to the 5th plus 3x cubed plus x plus 1. Okay, there's a function. Part A, show that it's invertible. And then part B, it's invertible, so I'll let G be the inverse. And I want to compute G prime of 6. Okay. The main kind of thing. If you can do this stuff, then I think you're in good shape. Okay, so what's the deal? Given a function, how do I show that it's invertible? Probably when you get a question like this, the point of that question is going to be try to show that it's monotonic. You don't want to try to solve for the inverse. That's probably going to be really hard. Probably the point is to show that it's always increasing or show that it's always decreasing. So the thing to recall is that if f is, say, is monotonic, which is just a stupid way to say it's always increasing or always decreasing, then it passes the horizontal line test, and therefore it's invertible. So this is what I want to show. How can I show that a function is increasing? We take its derivative and try to show that it's always positive or something like this. So first I would take the derivative. The derivative here is going to be 5x to the 4th plus 9x squared plus 1. And indeed, I have x to the 4th, x squared. These are both even powers of x, so both of these terms are going to be non-negative. So I have 1 plus a non-negative thing. The whole thing's going to be positive. So if it were me, I would say since 5x to the 4th and 9x squared are both non-negative, f prime of x is bigger than or equal to 1, so therefore it's positive. So this is exactly what we wanted to show. If the derivative is always positive, that means that f of x is increasing. So f is 1 to 1. That's what that shows, and therefore invertible. Part A done. We've shown that the function is invertible. And then in part B, we have to compute the derivative of the inverse at some point. Okay. Again, the point of a question like this, if you get it, is not to find the inverse function, because that's probably really hard. And you know, you could think about it if you want, but you'd have to solve a degree 5 polynomial for x. That sounds insanely hard. So the point usually of a question like this is that you want to use this fact about computing the derivative of the inverse, which in our case is 6. This is 1 over f prime of g of 6. And the idea is that this might be easier to compute. Probably will be easier to compute. Okay. Now, f prime we already have, right? So the only thing we need now is g of 6. if we can figure out g of 6, we're in good shape. What is g of 6? G is the inverse of f. So g of 6 is the thing that you feed to f to get 6. In other words, g of 6 is the solution to f of x equals 6. I lost my train of thought. Oh yeah, so we need to solve the equation f of x equals 6. Here's f of x. So we need to solve x to the 5th plus 3x cubed plus x plus 1 equals 6. How do you go about solving something like this? You're not going to do it algebraically, so the point here is to just guess the solution. That's what you're supposed to do. So I look at it, and I'm thinking, does 0 work? Nope. What's the next number I try? Probably 1. And if I did this in my head correctly, 1 plus 3 plus 1 plus 1 is 6. Okay, so we got lucky, we guessed, and we found that the solution, so by luck, x equals 1 is the solution. Which is to say g of 6 is 1. Okay, so then we can put all this together. G prime of 6 is going to be 1 over f prime of g of 6 was 1, which is 1 over, let's see, where was f prime? Oh, I erased it. Nice. But I think it was 5x to the 4th plus 9x squared plus 1. So this would be like 1 over 5 plus 9 plus 1, which is like 1/15. That would do it. Okay. So if you can do this kind of thing for inverse problems, I think you're in good shape. Oh yeah, okay, so then I was going to prove a reduction formula, and then I'll find the Maclaurin series for cosh of x squared. Which, you tell me, what reduction formula do you want me to prove? Oh yeah, we can do a complete the square problem as well. See ya. Is that what I said? Oh yeah, yeah, okay. Yep, that works. Yeah. Okay, we'll do the cosine to the n. So let me do this. Let me stop request for now, and then I'll see how I feel after I do reduction formula, cosh of x squared, and then a complete the square problem. I might be tired after that, maybe not, we'll see. Okay, so let's prove. This was one of your homework problems to, I think maybe last week. But we want to figure out the reduction formula for the integral of cosine to the n of x dx. Okay. Now, pretty much all of these reduction formulas, the way you start out is with integrating by parts. So we'll start out integrating by parts. Oops. Which means I need to call something u, and I need to call something dv. Now, what am I going to call dv? First of all, it has to be something that I know how to integrate. And I have n copies of cosine. What could I integrate? To me, the most natural thing to integrate is cosine. So if it were me, I would probably call dv cosine. What does that leave for u? Well, if I call dv one copy of cosine, there's n minus 1 copies left. So u would probably have to be cosine to the n minus 1. All right, so then we need du and v. Just going to check. Sorry, sending an email really quickly. Okay, let's see, if dv is cosine, that means v, I'm losing my mind, should be sine. Thanks, Jack. Here, to take the derivative of this thing, let me give myself a little bit more room. Power rule is going to give me n minus 1 cosine to the n minus 2 of x. Then take the derivative of the inside, which will be a negative sine of x dx. That's a little ugly to look at, sorry. Okay, there's my integration by parts setup. Let's run integrating. Let's use the formula. Integration by parts would say the integral of cosine of x dx is u times v is cosine to the n minus 1 times sine of x minus the integral of v du. Du has a negative n minus 1, so I can pop that out front. Minus 2. And then sine times sine is sine squared dx. Okay, so that's took me a little while, but that's one application of integration by parts. The next trick is we get, continuing from over there, I've got cosine to the n minus 1 sine of x plus n minus 1 times the integral of cosine to the n minus 2 times 1 minus cosine to the n, or cosine squared dx. Then I'll distribute this stuff onto each term. And here I would get an n minus 1 times the integral of cosine to the n minus 2 minus n minus 1 times the integral of cosine to the n minus 2 times cosine squared is cosine to the n. Okay. And then just like in that integration by parts problem that we did a long time ago now, we end up with an integral that we started with. And that's fine because I can just algebraically relate it back to itself to solve for that integral. So in particular, what we've shown is that the integral of cosine to the n is this stuff. Here's smiley face. Here's smiley face. Do the exact same thing that we did earlier tonight. Move this term over here, and then algebraically solve for the smiley face thing. So if I add this expression to this side, I would have this plus n minus 1 times this. That would give me n times smiley face is this stuff. Think we're good? Okay. Nice. Then all we have to do is divide by n, and that'll do it. So smiley face, which was the integral of cosine to the n, this is 1 over n times this, plus n minus 1 over n times the integral of cosine to the n minus 2. All right. Whew. There's the reduction formula for cosine to the n. Nice. Okay, what was next? Cosh of x squared. Well, here's the first thing I would check. Does Marco give us the formula for cosh of x on the final? No. Okay, so we'll just have to figure it out. So that what I would do to figure out the Maclaurin series for cosh of x squared. So compute the Maclaurin series for cosh of x squared. First thing I would do is just compute the Maclaurin series for cosh of x. Oh, but this might, I bet this is in the book. Maybe not. We'll just do it. So first, it'll be easier to find the Maclaurin series for cosh of x. Then once we have that, we can plug in x squared. We'll be done. Okay, so how do we find a Maclaurin series by hand? We just start computing derivatives. G of x is cosh. When we compute a Maclaurin series, we care about these coefficients at 0. So plug in 0 here. Cosh of 0 is 1. Sinh of 0 is 0. cosh of 0 is 1, sinh of 0 is 0, etc. So what we're finding here is that all even derivatives are 1, and all odd derivatives are 2. So let me write that down. I would say all even derivatives at 0 are 1, all odd derivatives at 0 are 0. So what does that tell me about the Maclaurin series? The formula for the Maclaurin series that we care about is the sum from k equals 0 to infinity of the kth derivative of 0 over k factorial times x to the k. Now, what we found here is that we only care about even terms. All the odd terms are 0, so who cares about them? We can ignore them, and we can only consider powers of x, which are even. Now, whatever power I'm looking at, I always get that power factorial down here. And then what is this relevant derivative? All even derivatives are 1. So I put a 1 there. There you go. That's the Maclaurin series for cosh of x. Then with that, we can figure out cosh of x squared pretty quickly. So f of x, which is cosh of x squared, what do? I just take this expression, and anywhere I see an x, I stick in x squared. That'll do it. X squared to the 2n is like x to the 4n, all over 2n factorial. Done. Okay. Okay, here's my plan. Arik wanted to do a complete the square problem. That's a good idea because I haven't done that yet. So I'm going to do a complete the square integral, and then I'm really tired, so I might call it there. I'll answer a few more Q&A questions after that, and then we can officially conclude from there. Okay, so one more example. Let's do give me a second. All right, let's do this. Yeah, I know. I should be getting a plaque soon. Yeah, so I would say between the 2 review sessions, I've covered pretty much everything you need to know, which is a lot, but that's like 7 hours of review sessions. But yeah, I think between the 2. Let's compute the integral. What did I just cook up? Then I've got to get ready for 2 32A review sessions in a couple days, so that'll be fun. X squared minus 4x plus 6. As usual, I'm thinking about all my options. Can I do any super obvious algebra? I don't know. Completing the square counts as algebra, but there's not anything super obvious like, oh, simplify powers of x or something like that. Would a simple u substitution work? Probably not, just because the simple u substitution I would think of would be the denominator, but then the differential won't work out on top. Okay, so then I move on to chapter 8 techniques. Do I integrate by parts? Probably not. Do I partial fractions it? Maybe. And then I think about if I'm going to do that, I need to factor the bottom. Can I factor the bottom? I don't think so. 6 and 4 don't really play well together. That may be true. So I don't think I can factor it. So I'm out of options, and this is where I think, oh, maybe I can complete the square and do some kind of trig thing. So let's do that. So maybe I'm thinking like, oh, factoring doesn't help. So I'll try to complete the square and see if that helps. Complete the square. How does that work? To complete the square, the algorithm is look at the coefficients in front of the x. In our case, that's -4. Take this number, divide it by 2, and square it. That's the thing that you want to add and subtract to complete the square. So here, this is -2 squared. So I would add a 4, but then I can't just add 4. I have to subtract 4 as well. And then I've got this plus 6. And then the idea behind this and the whole point is that now this chunk, this factors. And it factors as a perfect square in particular. Aw. I love you guys too. All right, so then if I factor that, I'll continue up here. I've got the integral of 1 over, in particular, this green chunk here, it looks like it's x minus 2 quantity squared. And then I've got 6 minus 4, which is a plus 2. Okay, and that looks like something that I know how to do, or that I can figure out. You could think about this as a trig substitution. But if it were me, I would think that, oh, I already know the antiderivative of, say, 1 over x squared plus 1. And this kind of looks like that. So I can rig up a simple u substitution to accomplish that. But if you want to do, you could do a trig sub as well. Here's what I would do. I would I would recognize that I already know that 1 over u squared plus 1 du, antiderivative of that is arctangent. So this is what I'm aiming for. To do that, I want this to be a 1. Factor out the 2. If you do that here, it would be plus 1. And then when you factor, and then I look at this and I think, gee, I really wish x minus 2 quantity squared over 2 looked like u squared. Wouldn't that be great? And this is what will dictate my substitution. So I would let u be x minus 2 over root 2, which I get by just taking the square root here. Then we're in the home stretch. Du is going to be 1 over root 2 dx. So dx is root 2 times du. So I'll get a factor of root 2 out front. Integral of 1 over u squared plus 1 du. Ding, ding, ding. That's arctangent. And then we are almost done. Okay, I'm going to awkwardly finish over here. Sorry about that. Got root 2 over 2, arctangent of u. Arctangent of, okay. Anyway, that's a complete the square integral. Okay, so I'm really tired, so I'm going to stop here. Like Cheney asked, I've pretty much covered everything you need to know in some capacity over the past 2 review sessions. So if you've been watching, you're probably in good shape. In general, for parting words for the quarter, I guess. Oh, my office hours tomorrow, I'm going to have to cancel. I think I maybe said that in an email. I'll send out another email tonight, but no office hours tomorrow morning. So this is goodbye for 31B. It's been a pleasure. Good luck tomorrow. Don't worry too much. You'll be fine. If you're taking 32B next quarter, definitely keep an eye on the YouTube channel because all stuff is going to be on there. If you're taking 32A next quarter, I already, in the past like 4 days and for the rest of the week, I'm going to be uploading a lot of 32A content for my students right now. So you can keep an eye on that. Or if you want, you can zoom into my 32B office hours just to say hi. Next year sometime. Okay. I'll answer a few more Q&A questions if you want, and then I'll sign off. I'll eat some more gummies. I'm actually really sad because this could be my last 31B class. Maybe not, but I don't know how my teaching will shake out next quarter or next year. So this could be my last 31B class, which is really bittersweet. Actually, it's not bitter at all, or it's not sweet at all. It's just sad. 31B has been a big part of my life the past few years. So I did eat dinner today. I got Panda Express. That's where I got my fortune cookie. I could eat oatmeal for the rest of my life. I have oatmeal every single day. I could, yeah, I'd go with oatmeal. Do I have any advice for math majors? One of the best things that you can do, especially once you get into upper division classes, is, and it sounds a little silly, but read the textbook. I think that's a thing that not many people do, but textbooks are great and they're there for a reason. So you really want to read the textbook, and then the same kind of advice that I've given all year long for those of you guys that have had me since the fall is practice, 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 practice. The more problems you can do, the better. If UCLA would hire me, I would take that in a heartbeat. That would be like a dream come true. So if you can make that happen, I will be forever grateful. I just want a job somewhere that I can teach. How many years have to pass to get a drink with you? Well, to be honest, I don't really drink much at all anymore. I'll think about that. Which state is superior in the US? I mean, I'd have to say California. I don't know. There's so much nature. There are cool cities. California's pretty sweet. Ohio's fine, but I don't know. I don't know if I love Ohio. I'll go with California. Jennifer, maybe I'll say by the summer. Probably wouldn't be weird in this. I don't know. Not sure. Okay, one more package of gummies, and then I'm saying goodbye. None of you guys are here to eat all of my candy that I have, so I have to eat it all. That'll be exclusive YouTube content. Maybe I'll upload a video. Although we can't go to the gym at all right now, so. Probably 2 more years. I'll be here for 2 more years, I bet. As long as I can get funding for 2 more years. But you'll see me around. You can come say hi in my office when we're all back on campus. Okay. I'm going to call it there. Goodbye, everyone. Good luck. Get a good night's sleep. That's my main piece of advice. Okay, farewell. All right. Signing off. I don't want to end it. All right, I'm ending it.